this chapter, we will be looking at various types of functions. In this lesson, we will be looking at the characteristics of polynomial functions.
Okay, so here we go, taking a look at polynomials. So the first thing we're going to do is introduce the concept of a polynomial function and the common way we're going to write this here. So I'm going to zoom in on this a little bit here. Now I know that for most of us here, you're going to be familiar with the concept of a polynomial. We just want to kind of be more specific about it. A polynomial is going to be written in this form right here. Okay, where f of x is going to equal a sub n times x to the n plus a sub n minus 1, x to the n minus 1, and so on. Okay, all the way down to a sub 1 times x plus a sub 0. Now, I know that that might look like an overcomplication of what this is, but actually it's not. Couple of things here. We're going to let n be an element of the wholes, okay, meaning that n can be anything from 0 up to whatever natural number you'd like here, but we're including 0. Now, we're including 0. Technically, what should be happening here is at the very end here, this should be x to the 0, okay? Because n is going to refer to the exponent on the variable x. And then a can be any real number here. Now, notice that we've got these a sub n minus 1. The subscript here is just an index. Okay, a sub n, the only reason we use that is so that we know that this particular value goes with x to the n. A sub n minus 1, we know that that goes with x to the n minus 1. So down here, a sub 2, we know is the coefficient of x squared. That's why we're using this particular notation. We're using a for all of them, for all of the coefficients, because if we were to use other letters in the alphabet here, like A, B, C, well, we're going to run out really quickly. It doesn't take us long to create a polynomial that's got too many terms there to be really useful there. So we're just going to use A to refer to the coefficients, and then the subscripts, and the subscripts help us connect it to that particular value there. Okay, but essentially we've got just powers of x. Okay, and essentially, if you want to think of it this way, you can think of it like this: positive integer exponents on x, and then real coefficients. Now let's talk about, let's zoom out a little bit. Let's talk about what a polynomial might look like. So here's a good example. Y equals negative 2x cubed minus 5x squared plus 4x plus 7. So think of it like this. We know in this case right here that a sub 3 is going to equal negative 2. A sub 2 is going to equal negative 5. A sub 1 is going to equal 4, and then our constant a sub 0 is equal to 7. Okay? We know that the degree of this function is 3. Now, degree, you've been looking at degree for a long time here. You look at each individual term here, and you take a look at the exponents, okay, of all the variables, and you look at the highest value here. So the degree here is 3, the degree here is 2, 1. The highest degree over this overall function is 3 here. Okay, so it's the highest exponent. And now we're going to look at a context as to why this is important. Prior to this point here, we would talk about degree, but we wouldn't exactly tell you why it's significant, what the issue is. Now, I want you to know here that this has to do with the shape of the corresponding graph. Okay? Let's take a look at the leading coefficient here, negative 2, so a sub 3 is equal to negative 2. The reason why that's significant is because that gives us a direction of motion for this particular graph. Whatever the graph looks like, the leading coefficient is going to give us an overall sense of which direction this graph is moving. And then finally, the constant, okay, the term here that doesn't have the variable in it, that is actually going to end up being the y-intercept of the graph here. Now that makes perfect sense if you think about it. As the thing about the y-intercept is a point where x goes to 0. If x goes to 0, this term goes away, this term goes, in fact, every term with a 0 in it goes away. All you're left with here is the 7. So that value there becomes the y-intercept. This is about the position of the graph. Okay, so the constant gives the position, the leading coefficient determines the direction, and the degree determines the shape of the function. Okay, now let's have a quick look at just some examples of things that are polynomials and things that aren't here. So g of x equals 2x minus 1, that's a polynomial. X squared plus 3x plus 2, that's a polynomial. Okay, it doesn't matter that the coefficient here is a fraction, makes no difference because it's just got to be a real number. So that's a polynomial. Over here, a single term like that, boom, still a polynomial. Now compare that to these examples down here. This one is not a polynomial, and the reason it's not a polynomial is because of the exponent right here, that -3. In a polynomial, the exponents should be positive integers, okay? Or 0 if you want to think about it as this being x to the 0 at the end here. That's negative. This is actually a rational function because that x cubed would drop, x to the -3 would drop into the denominator as x cubed. Rational. This one here is an absolute value function. Okay, it's not polynomial. Although this can be broken up into two piecewise, two functions here that are polynomial, but it would be a piecewise function. Okay, so it doesn't strictly follow the example that we're setting up here. H of x equals 1 over x squared. Well, that is definitely a rational function. If you were to bring that up, you'd get x to the -2. And again, that's the problem with the exponent. That should be positive. Y equals 3 to the x plus 5. Now this is a different one. The x in this case, the variable, is up in the exponent. That makes this one exponential. Okay, so this one right here is rational because we got the x in the denominator. This one's exponential because the x is in the exponent. Here, the exponent on the x here would be 5/2. Okay, remember that radical introduces a 1/2 in the exponent. That's going to be x to the 5/2. That makes this particular expression right here a radical function. And because the x here is in the radicand. Now, if this was, for example, the square root of x to the 4th, that would still be polynomial because I can simplify that. I can take that down to x squared. But this one I can't. I'm not going to be able to get that any cleaner than that x to the 5/2 there. Okay? So I'm always going to have, in this case here, this fraction in the exponent. I'm not allowed to have that for a polynomial function. That would be radical. But those are the things we're looking for. It's the position of the variable. Okay? If the variable's in the denominator, it's rational. If it's in the exponent, it's exponential. If it's in a radical, it's a radical. Okay? If it's in the radicand of a radical, it's a radical function. We are looking for x to have positive exponents. Okay? Positive integer exponents.
Now we were going to take a look at the different types of polynomial functions.
Okay, so now what we're going to do here is just take a quick look at how degree affects the shape of polynomials. So we're looking at types of polynomial functions, but we're really looking at the effect of the degree. So right here, if our degree is 0, we call that a constant function, okay? And it's just a straight horizontal line. If our degree is 1, then we're going back. This is what we would have seen in Math 10. We're just looking at a linear function, okay? Just a nice little straight line there. As long as it's not horizontal, because if it's horizontal, then it's just a constant. But it also can't be vertical, okay? Because a vertical line, okay, a vertical line isn't a function. Okay, so a horizontal line would be considered constant, but a vertical line isn't a function, so we're not considering that here right now. Degree 2, we spent a lot of time in Math 20, okay, grade 11 here, looking at quadratic functions here, so we know what those look like. Okay, degree 2's open up or they open down. Okay, but they've got that nice characteristic shape here. Notice that as soon as we've got a degree 2 here, as soon as the degree is 2, we've got a point here on the graph where the graph changes directions. Kind of interesting. We're going to come back to that in a second here. A cubic, degree 3. Okay, degree 3, this is a very stereotypical look at a degree 3 function. It doesn't have to look like this per se, but it's definitely going to have this kind of a, or at least a hint of a wobble in it right here. Okay, now notice that it's got 2 points where the graph changes directions, goes up, changes direction, comes down, goes up again. Now, it doesn't have to have 2 points of turning, okay? But if it's a cubic, it will have no more than 2. 2 is its maximum, okay? So we can stretch this. We've seen earlier in this course, we talked about transformations. We can stretch this thing so that it doesn't have a point where it changes directions here, but we certainly can't manipulate this so that it has more than 2 and yet still be a cubic. Degree 4 is called a quartic function. Okay, 4th degree here. notice that at maximum it's going to have 3 points where the graph changes direction. So here it drops, changes direction, goes up, changes directions, drops, changes directions, goes back up again. Again, it can have no more than 3 of those. It can have less, but no more than 3. But that's what, again, a stereotypical little quartic function looks like. And this is the quintic here. This is the highest degree function that we're going to consider in this course. Now, as we go through the examples, you might see us look at larger ones here, but on the diploma exam, on the final exam, there won't be anything higher than this, okay? And you'll see here that at most, this one's got 1, 2, 3, 4 spots where it changes directions, and that becomes the defining feature. Another thing about this is notice when it was degree 5, it started low, this graph extends infinitely down, wiggles around, and then it goes up, okay? That's a degree 5. Now, a degree 4, it started from above, it came down, and then it went back up again. So it returns kind of in the direction it came from. A third degree doesn't do that. Started low, it's going to end high. Second degree, started high, ends high. It goes back where it came from. A linear function starts low, goes up. So you should be seeing a bit of a pattern here, or a connection between functions that are even degree and functions that are odd degree. We're going to explore that more in a little bit.
In this section, we're going to look at the different characteristics of polynomial functions that are of odd degree.
So now let's take a little bit more of a closer look at what happens if you've got an odd degree. Okay, so an odd polynomial here. Specifically, let's take a look at what you have a positive leading coefficient. So I know that if you've got, for example, this is a cubic here. I know that if you've got an odd degree, you're going to have the number of turning points will be 1 less than the degree. That's no different than an even degree. But notice what happens with an odd one here, particularly with a positive leading coefficient. The graph here starts in quadrant 3, eventually ends in quadrant 1. In other words, it moves upward. Okay, the general motion here is up. Even here with a 5th degree, okay, the general motion here is up. Starts in the 3rd quadrant and eventually ends in the 1st quadrant. Okay, and that's exactly what we're seeing over here in our description here. The graph extends from quadrant 3 to quadrant 1. There are no absolute max or min points here on this particular graph, although if you're in a calculus class, you would have discussed there are the presence of locals, okay, or relative maxes and mins here. But in this course here, we're only interested in the presence of the absolutes, and there are none if it's odd. Okay, the number of possible x-intercepts is from 1 up to the degree. Okay, let's take a look at what we mean by that. So notice that this here, I know that this is a cubic because it's got 2 turning points. At least it couldn't be any more than a cubic. I'm sorry, it could be more than a cubic. Cubic is the absolute minimum that it could be. Notice that there's only one spot there where it goes through the x-axis. Okay, over here, this is a 5th degree, and it's a little hard to see what's going on here. I suspect that it dropped below and went back up again. There's 1, 2, 3, 4, 5, okay, different x-intercepts here. There could be no more than that though, because you'll notice here the graph at no point ever is going to come back around again. Okay, this is the maximum number of turning points. That's the maximum number of times it's going to hit the x-axis. The domain is going to be all reals, and so is the range. Now, if you change this to a negative leading coefficient, what that does is cause a reflection over the x-axis. But essentially what this means is that the general motion of this graph is going to be down. We're going to start in quadrant 2, and eventually we're going to end in quadrant 4. Quadrant 2, end in quadrant 4. And that's again what we're seeing right here. Okay, we call that the end behavior. Okay, how are the ends of the graph behaving? Again, there's no absolute max or mins. The number of x-intercepts is from 1. You got to have 1. Okay, but up to a maximum of the degree, same number as the degree. The domain is all reals, and again, the range is all reals. Okay, so that's how you got to think about or the characteristics that you need to associate with an odd degree polynomial.
In this section, we will look at the characteristics of polynomials that are of even degree.
Now we're going to change it up and look at what happens if the degree is even. So now, and this one here should be really familiar to everybody here. This is a parabola. This is degree 2. Now, to use the same language that we used in the previous one here, notice that I start in quadrant 2 and end in quadrant 1. Okay, same thing here for this one. This is a quartic. This would be a fourth degree. I start in quadrant 2 and I end in quadrant 1. Now, essentially what happens here is this thing is opening up. Okay, and if you want to think about it, if you need some help here, it's a positive one. So look at that. Happy face. Oh, so smiley. Okay, so positive. Okay, opens up here. Now, this means, here we go, the graph extends from quadrant 2 to quadrant 1. We just said that. It contains an absolute min. For each of these graphs here, there is a point on the graph that would be considered the lowest point. Now, bear in mind, this is vertical. Okay, the y-axis or the y direction there, that's considered vertical here. So this is considered the lowest point on the graph. That would be the absolute min. This is considered the lowest point on the graph. That one there is the absolute min. Okay, every time you've got a positive, even degree function, you are going to have a point like that show up. The number of possible x-intercepts is from, this time it's from 0 up to the degree, okay? Because all I would have to do is shift this graph up above the x-axis and then it no longer touches the x-axis. There's no more x-intercepts here. However, this is a degree 2 and I can see that right now I'm hitting it twice, okay? This is a degree 4, but I'm still only hitting it twice. So it's not that I have to hit it either 0 or the degree. It can be in between there. But the maximum number of times that you're going to hit the x-axis will be the same number as the degree. The domain is going to be all reals. And the range, and right here, that depends on the min value. So whatever your min is, so if, let's say, if y equals a is the min, okay, then the range here would be greater than or equal to a. Okay? Now, let's just change the leading coefficient. Let's make it a negative. And just like with the previous discussion here on the odd degree ones, that causes a reflection over the x-axis. Okay, so now notice again that we start. We're going to talk about the end behavior. Starts in quadrant 3, ends in quadrant 4. Starts in quadrant 3, ends in quadrant 4. Now the reason I say start end because we're always reading this left to right. Okay, always going to read things left to right here. So someone's going to ask, couldn't I have started over here? Yeah, but we don't do that. Okay, we read it left to right. Then these things are going to have this absolute maximum point here. Okay, and every one of them is going to. So again, from 3 to 4, it's going to contain an absolute max. Same as the positive one here. And actually, sorry, I can help you out with this too. If you want to think of it negative, you could think of it as negative and sad, right? Because it opens down. And that might give you a little bit of an indication as to what quadrants you're starting in and ending in here. The number of x-intercepts, again, is from 0 up to the degree. The domain is going to be all reals. Okay, and then here again, let's say that my maximum value, so let's say y equal to a is a max. Okay, so then my domain here, my range, I should say my range is going to be less than or equal to a. Whatever that maximum turns out to be, that's what my range is going to look like. So it depends on the graph there to a large degree. Anyway, those are the properties that you got to be considering when you think about a positive or negative even degree function.
For each polynomial function, state the degree. If the function is not a polynomial, explain why.
Okay, so let's jump right in here. So take a look at h here. This is going to be degree 2, but this is not poly. Okay, the reason it's not poly is because I've got a variable. My independent variable shows up underneath a radical. This is a radical function. Okay, let's move on. This one right here, this is a degree 3, and this one is a poly. Okay, notice that the exponents on the x, they're all positive integers. There's nothing else going on. There's nothing weird. It's not like they're in the x's in the denominator or x's in the exponent or anything like that. It's awesome. It's exactly what I needed it to be. Whoops, whoa, went too far. Negative 8x to the 4th. Okay, well this is degree 4, and this is in fact a poly. Now, some people are going to argue, how can it be a polynomial if there's only one term? Okay, polynomial is just this general expression that we give to all of those things. So yeah, that would encompass this as well. So don't fight with that one there. Just accept that there. And this last one here, again, this is degree 2, like the first one, but this is not a poly. Okay, because we have an x in the denominator here, this would probably be better described as a rational. And if you didn't like seeing it like this and think, well, I could bring that up, yeah, you could bring that up, and that would become x to the negative 1 minus x squared. But you're still going to end up with a value or an exponent here that's not a positive integer. Okay, so again, it still wouldn't fall into the category of polynomial. That's definitely something different. And we call this one a rational.
Complete the following table.
Okay, so to fill in this chart here, I'm just basically going to run down the columns here. So for this first one here, the leading coefficient, I'm looking for the value, okay, the coefficient in front of the term with the highest degree in it, okay, or the highest degree term here. So in this case here, this is a square, and actually I can do the degree right now. This is a second degree function because it's 2 here, and the leading coefficient is 4. This one here is written out of order. This is the term with the highest degree. It's degree 3, and its coefficient is 4. So that's the leading coefficient. Don't get stuck thinking that that leading coefficient has to be the first one. Okay, the leading coefficient is the coefficient of the highest degree term. Down here, just compare the exponents there. So I know this is a 4th degree function. The leading coefficient here is negative 1. This one here is a 5th degree function, and its leading coefficient here is going to be negative 4. Oh boy, this one here. Now, okay, I want you to think this one through here. I'm not going to expand this out. I don't want to expand this out. However, if I were to expand it out, I know that this would produce an x squared in it. Okay? This x plus 3 squared would produce an x squared. Now I'm going to multiply that x squared by negative 2x, and then I'm going to multiply it by this x. So I'm going to have x times x squared is x cubed times x is x to the 4th. This will end up being a 4th degree polynomial. And the leading coefficient, well, okay, the coefficient here is 1. 1 squared is still 1. The coefficient here is 1. But the coefficient here is negative 2. So that negative 2 is going to get multiplied by that 1 and the 1, so it's still going to be negative 2. That's how you'd kind of think that one through here. Now this one down here, a little bit more complicated because of that 2 right there. But let's walk it through again. I've still got this 3 out front. Now again, I'm not going to expand this whole thing out here because that's just a lot of work here. But I know that if I was to start it, the first term here would be 4x squared. Okay? And there'd be other terms here. Over here, this is going to be the x. And I don't really care about the minus 1 right now. When I multiply these together, I'm going to get a 4x squared times an x. Well, that'll be an x cubed. So this is going to be a degree 3. The coefficient here is 1 times 4 times 3. The leading coefficient here is going to be 12. Okay? So there we go. And so all I'm kind of doing here is picking out of there, without expanding the whole thing, I'm picking out the piece that I need. Now, let's run through here real quick. This is odd, whether it's odd or even. Okay, once you've got the degree here, this is going to be pretty trivial. This is going to be even, odd, even, odd, even, odd. Okay, 2, 3, 4, 5, 4, 3. All right, now end behavior. End behavior is basically looking at what happens whether this is even or odd and what the leading coefficient is. And when I say what the leading coefficient is, I mean whether it's positive or negative here. So right here, this is a positive even, so this is going to go from 2 to 1. That's what we mean by end behavior. Okay, what quadrant do I start and what quadrant do I end in? Okay, this is a positive odd. Okay, so this is going to go from 3 to 1. This is a negative even, so this is going to go from 3 to 4. Okay, it's going to open down. This is a negative odd, so this is going to go from 2 to 4. This is a negative even, so again, it's just like the ones a couple up here, so it's going to go from quadrant 3 to quadrant 4. And this is a positive odd, so it's going to go from 3 up to 1. And again, that's what we're talking about. When we ask about end behavior, I'm asking about what's going on at the far extremes of the graph, to the far left of the graph, to the far right of the graph. Okay, maximum number of possible x-intercepts here. Now, maximum number. Now, it should have been clear, based on the characteristics of the polynomials that we're looking at, that that's related to the degree. This is the degree. So this would be 2, 3, 4, 5, 4, 3. That's the maximum number of x-intercepts that these things could possibly have. Okay? Now, my y-intercept. Okay, well, the y-intercept is, I want to be able to see the function here, so I'm going to kind of push this over. I got to think, what would happen here if I let x equal 0? Well, in this first one, if you let x equal 0, I'm left with 8. That's my y-intercept. And additionally here, everybody, that's also going to be the constant term here. In this next one, if I let x go to 0, all that goes to 0, I'm left with -2. And that turns out that's going to be my constant term as well. Here, again, let x equal 0, I'm left with 5. And that turns out that is my constant term. Let x equal 0. Oh, everything goes away. Now don't get thrown off by that. That just means that the y-intercept here is 0. And that is kind of my constant term. There is no constant term. It doesn't show up, but that's because the value is 0. Okay? You wouldn't write it if it was 0. So there you go. Now, this one right here. Oh, this one. If I let x equal 0, okay, everybody, notice that this x right here is going to cause everything to equal 0. So, my y-intercept here is going to be 0. Now, does that necessarily mean that my constant term is going to be 0? Kind of looks like it, because they've been the same all the way down here, but let's just think about this. Let's cover up this first term here. If you were to expand this thing out, just this last little bit here, this x plus 3 squared times the x minus 1. The constant term coming out of this would be 9. The constant out of this would be -1, so multiplying those together would be -9. Okay, and that would be the constant. But now we've multiplied by a -2x. That -2x is going to distribute to every term, including the -9. And so what we're going to see here is every term is going to have an x in it. So this is going to be very similar to the one just above it. And so yeah, it turns out the constant term would be 0. There really is no constant term at the end. Okay, and so the value there would be considered 0. Now compare that to this next one. If you let x equal 0 here, you're going to get 2 times 0 is 0, plus 1 is 1, and then 0 minus 1 is -1. So multiplying that out, I'm going to get 3 times 1 times -1, or -3. Now at this point, I'm very tempted to assume that that's going to be my constant term, but let's just think about it here. If I expand this out here, just this 2x plus 1 squared, if I expand that out, the constant that's going to come out of this is going to be a +1. It's going to be at the very end here. If I was to multiply this out by this one right here, I would end up with +1 times a -1. So then my constant becomes -1. And then my 3 gets distributed to every term. So 3 gets multiplied by that -1 to get -3. There it is. There's my constant term. And it is the same as the y-intercept. Awesome. Now, I got to ask, will these things have a max, a min, or neither? In other words, I'm asking, will it have a maximum, sorry, an absolute maximum, an absolute minimum, or neither here? That has to do, okay, with the degree. So if it's even, now, sorry, it has to do with the degree and the direction that it opens here. So I have to look at the leading coefficient here. So I've got a positive even. So this is going to have a min. It's going to open up. Okay? Positive, even, happy face. I've got a positive odd. Okay, positive odd is going to have neither. In fact, I can jump ahead here. This one was odd, and the last one here was odd as well. So these are going to have neither a max nor a min here. Okay, so let's take a quick look at this. This third one here, this is a negative even. So negative even, remember, negative even, it opens down. It's so sad. So it's going to have a maximum. Okay, this up here was the minimum. This is a maximum. And finally, in this chart here, I've got a negative even, again opening down. So again, it's going to look like that. And so this one is going to have a max. All right, there you go. I hope seeing that all together and seeing how these things develop, okay, as we pull this information out here, I hope that all makes sense and gives you a better sense of what these things look like without even having to graph them.
On each set of axes, sketch a polynomial function with the given characteristics.
Okay, so the first one says a polynomial function with degree 3, so it's going to be a cubic, so it's going to have the 2 turning points in it, a positive leading coefficient, okay, that means it's going to be moving up, okay, and 2 x-intercepts. Okay, now I got to think how that's going to work here. So I know it's going to start low and it's going to end high. So it's going to come low, it's going to come up here. Now I just hit the x-axis once. I know I'm going to turn directions here. Okay, now if I come straight through and go back up again, I'm going to hit the x-axis 2 more times, and I'm not supposed to do that. I only want to hit it once more, so I got to come down, just touch it, and then go back up. Okay, and there we go. There's a cubic, a positive cubic with 2 x-intercepts. Now I want a polynomial function with degree 4, a negative leading coefficient. Okay, so that's going to come up and then drop back down again, okay, because it's going to be negative. Okay, it's even, degree 4, negative, opening down, and 4 x-intercepts. Oh, okay, so I'm just going to hit it the maximum number of times. So it's going to come up, it's going to come down, it's got to go through it again, I got to go back up again, because I'm supposed to have 3 turning points here for a degree 4, and then go back down again. So I've got this little kind of M shape here, and again, I'm hitting it 1, 2, 3, 4. Okay, that's pretty easy to do when they let you, when the number of x-intercepts is the same as the degree. Okay, I just kind of let each of my little wiggles here cross through the x-intercept, the x-axis. A polynomial function with a degree 5, okay, a negative leading coefficient, so a negative leading coefficient, this thing's dropping down, okay, a negative leading coefficient, and 3 x-intercepts. Okay, well let's think about how this works here. So with the degree 5, I'm going to have 4 turning points here. So I don't know, let's go through the x-axis once, twice, 3 times. Now, there's my 3 x-intercepts. I've only got 2 little wiggles here, so I need 2 more. But I've already hit the x-axis the number of times that I needed to. However, notice that I know that this thing is supposed to end in the 4th quadrant. I'm already in the 4th quadrant, so I'm actually just going to do this. I will create another wiggle, but I won't let it go through the x-axis, and so now I keep my 3 x-intercepts. It's a 5th degree negative leading coefficient. Now, this isn't the only way that this could be drawn. I could have had that extra wiggle up here, like a little wiggle, and then hit it 3 times. I could have come through, hit it here, gone through, hit it like that, and come through so that, basically so that this point right here was on the x-axis, this point was on the x-axis. It doesn't really matter here. They're not giving us any more information than that. There are other ways that you could have done this for sure. Okay, let's take a look at this last one here. A polynomial function with degree 4, a positive leading coefficient. Okay, so it's a degree 4, it's positive, so it's happy, it's going to go up. A leading coefficient and 2 x-intercepts. Okay, actually, sorry, this one is describing a scenario very similar to the one that I was just indicating we might have done here. So it's going to start, it's going to come down from the left and going to go back up to the right here. So it's going to come down in the 2nd quadrant, up in the 1st. In order for this to work here and have just 2 x-intercepts, there's 2 ways I could do this. One is to have it come down like this and just touch it. Come down and just touch it, and away we go. Okay? But another way that this could have happened, okay, another way this could have happened is this could have gone down through the x-axis like this, and then this turn up here, because I have to have another couple little turning points here, could do something like that. And so now these don't even hit the x-axis. These are my 2 x-intercepts, these ones don't. So there's a couple of different ways that you could do this. You could have flipped this the other way so that this one is up above and this one goes down and hits it twice. In either way there. So anyway, there's a little bit of freedom there. As long as it's obeying the rules that I'm given here, that's what we're looking for.
A toaster oven is built in the shape of a rectangular prism. Its volume, V, in cubic inches is related to the height, h, in inches of the oven door by the function V of h is equal to h cubed plus 10h squared plus 31h plus 30. What is the volume in cubic inches if the toaster oven, if the height of the oven door is 8 inches?
Okay, well, this question here is really just about evaluating. So we're going to take the V and evaluate it at 8. And there's my function right there. And so what I'll do here is I'll go to my calculator and I will enter this in. I'm actually going to show you 2 different ways of doing this. So first of all, I'm going to just plug this in for h. So it's going to be 8 cubed plus 10 times 8 squared. What is that? Plus 31 times 8. Yeah, plus 30. Press enter, and I get 1,430. 1,430, what is it? Inches cubed. That's one way of doing this. Now, there is another way of doing this, and I want you to see this here. I'm going to go into y equals, Okay? And I'm going to enter this in, but I'm going to put x instead of h here. So x cubed plus 10x squared plus 31x plus 30. Okay, enter that into my function here. Now, I could graph this. Okay, I could graph this. Oh, sorry, I did something with my window settings. I got to make sure. Okay, I'm going to go back to my standard zoom settings here. So I could graph this. Now, notice that I want to put in here where x is equal to 8 here. So I'm going to go to my trace menu. I want to figure out what's going on here when x is equal to 8. Okay, now notice that over here, this is where x is equal to 8. The function is way, way above it. Okay, that's okay. As long as the function isn't to the right or the left of the screen, that's okay. The calculator should have no problems with that. And in fact, it does. It gives me the 1430 right there, which is what I found previously. That's okay. Here's another way that we can do this. We can quit here. Because the calculator understands function notation. If I press my vars button right here, okay, vars, tab over there to y vars, choose that. I entered the function into y1. If I now go parentheses 8 parentheses, the calculator understands this to be evaluate that function where x is equal to 8. And again, I get the 1430. Okay, so there's just a few different ways that we could go around getting that particular number for this specific problem.
A piece of cardboard measuring 30 centimeters by 20 centimeters is used to create an open box by cutting out a square with length x centimeters from each corner, as shown in the diagram below.
Okay, so the first question here says write an expression for the volume of the open box here. So we're going to fold up those sides here. Now, I'm chopping it here. Sorry, you want to probably see this. I'm going to kind of not chop it here, but I'm going to fold along these lines here. And so this is going to fold up, this is going to fold up, this is going to fold up. So my box is really only that wide, and it's really only going to be that long. Now, the pieces that I'm cutting out here are all going to be x by x. So think about my length here. My length is going to be 30 centimeters, but it's going to be less this one because I'm going to fold that up. It's going to be less this one because I'm going to fold that up. So my volume here is going to be the length, which will be 30 centimeters, but minus 2 x's for either side. My width, which is 20 centimeters, but again, it's going to be less this x, so it's going to be 20 minus 2x. And then the height, okay, when you fold that up there, well, my height is actually going to be, it's going to be pointing x up, so my height is going to be x. So there's my expression for the volume of the box. Now, I could multiply that through, but I really don't need to. The next question here says, use your calculator to graph the domain, the function representing the volume. Okay, so let's go to y equals, and I'm going to enter in here 30 minus 2x, 20, whoops, sorry, I got to put parentheses there, 20 minus 2x, and then x. Okay, now I'm going to graph that. I haven't done anything to change my window settings. Whoa, and I get this really, really steep line here. Okay, so now I got to adjust my window settings here so I can see what the function is going to be. Let's just take a quick look here and think about this. So x here, I think it should be clear that x really has to be greater than or equal to 0. If x is equal to 0, the size of the squares I'm cutting out is nothing. Basically, it's just a flat sheet of paper. Which is fine. Hey, if that's what you want to call a box, knock yourself out. But it probably should be bigger than 0 here. But what's the maximum x can be? Well, let's take a look at it. This is 20. I'm going to keep cutting stuff out here. I'm going to cut squares out of this. The largest that I can cut them out is going to be 10. Because if I cut 10 centimeters this way, 10 centimeters this way, I've basically cut this piece of paper in half. If I come at it from this direction, the largest that I could get is going to be 15, because if I come 15 in this way, 15 in this way, I meet the middle, I'm cutting it in half. So my natural restriction here is going to be less than or equal to 10. So now I'm going to go back to my calculator here, and I'm going to make my window settings. I'm going to go from 0 up to 10 here. The range that I'm looking for here, if I graph that, now there's my, see the little bit of blue there? I don't see anything else, but the calculator's still thinking, oh, and I see just a little bit of blue on that side there. So my y, my range has got to be quite a bit bigger. It's got to go quite a bit larger than 10 here. I don't know. Let's try 500. Let's see what that does. So that was quite a jump there, but at least I'm seeing more of the curve. Okay, so this has got to be quite a bit larger. Let's make that 5,000. Okay, 5,000 was maybe a bit much here. So what do we say here? Let's make that 1,500 maybe. Okay, that's a better look at that graph there. Okay, but this makes sense. Now, I can see that this graph is going to dip below here, but this is the only domain that makes sense in this problem. Okay? Now, it says determine the length of x that would produce a maximum volume. What is the maximum volume? Okay, well, between 0 and 10 here, this is the only domain here that makes any sense. Anything beyond that really doesn't make any sense because it doesn't fit the diagram. So this is the maximum right here. So to find that, I will go into my calc menu, so second calc, and I'm going to be looking for the maximum here, number 4. And the calculator is now asking for a left bound. So what I'm going to do here is move that cursor so that it is to the left of that maximum. Then it asks for a right bound, so I pressed enter and hit that little line there. Now it's asking for a right bound. I move to the right of it. So as long as the maximum shows up between these two lines here, when I press enter, now it's asking if it can make this as a guess here. I don't really care what it guesses. So press enter. And it takes me to the maximum value here. Now the maximum value occurs, now it's hard to see that, where the x is 3.9. Okay. So my x is going to be approximately 3.9. And the volume, well, if you look back here, the volume that I'm getting is 1,056.3. So my volume is going to be 1,056.3. Now these are all in centimeters. So this would be centimeters, and the volume here would be centimeters cubed. Good. Now, determine the value or values of x of the box that would have a volume of 500. Well, I'm giving you a y coordinate here. So what I'm going to do is go down here, and I'm just going to enter 500 as the volume here. So this is my expression for the volume. This is a specific volume I'm looking for. And when I press graph, there's two spots where those intersect, where the 500 meets the actual volume of my box here. So I'm going to go into my calc menu, so second, trace. Now I'm going to look for the points of intersection here. Now to do that, I'm going to find the one on the left here first. I'm just going to move my cursor really, really close to that point of intersection. Doesn't have to be right on, just close. Am I on the first curve? Yep, press enter. Did I jump to the second curve? Yep, press enter. Calculator's asking if it can use this number as a guess. Yeah, sure, whatever. And what I get here is the the x value is 0.99. Okay, so x could be 0.99, now approximately. And that's one solution. Now, the other solution is going to come from over here, and again, I will go into my calc menu, grab my intersect. This time I'm going to move the cursor close to that other point of intersection. Let it go over there. It doesn't have to be right on, just close. Press enter for the first curve, enter for the second curve. Press enter, let it guess that. And I get 7.77 is another value that will give me a volume of 500 centimeters cubed. All right, so hopefully that gives you a sense of how to attack a problem like this box problem.